Solving this question, 3 raised by the power of t plus 9 raised by the power of t plus 27 raised by the power of t equals to 14, and we have to find the value of t. Solution. This type of question can be started at any side of the equation. We can start from the left hand side, and at the same time we can start from the right hand side. Therefore, I'm going to start from this left hand side. So what am I going to do? I'm going to rewrite this left hand side in an index form. Now I say 3 is already in its prime number, so I'm not rewriting that. It's still 3 raised to the power of t, then plus 9 is going to be written in an index form because 3 multiplied by 3 equals to 9, so which is 3 square. So I have 3 square here, then this power of t is still there, having some nice time, then plus 27 is 3 multiplied by 3 which is 27, and which is 3 raised by the power of 3. So instead of writing 27, I'm writing 3 raised by the power of 3, then the power of t is still there, and this is equals to 14. Then there is need to apply a certain index rule to this power inside the parentheses, then and t that is outside the parentheses according to the rule. If we have x raised by the power of m in parentheses, then still raised by the power of n, this can be written as x raised by the power of m times n, which is equal to x raised by the power of m n. Applying the same rule there, so my equation can now become 3 raised by the power of t plus 3 raised by the power of 2t, because 2 times t is 2t, then plus 3 raised by the power of 3t, because 3 times t is going to give me 3t, and still equals to 14. The next thing I'm going to observe to this left hand side is that I have the same base 3, 3, 3, and at the same time my power, that is the exponent, is an increasing order of 1. So this is 1t, this is 2t, and this is 3t. They are consecutive and by increasing order of 1. Then the next thing I'm going to ask myself is that, is there a way of rewriting this 14 so that it can form a pattern of this left hand side, that is having the same base, then having a power that is consecutive in an increasing order? This is what I'm saying. 14 can be splitted into 2 plus 4 then plus 8, because 2 plus 4 is 6, then 6 plus 8 is 14. Having this can be written having the same base with the order of consecutive power. What am I saying? 2 is 2 raised by the power of 1 in an index form, plus 4 is the same thing as 2 raised to the power of 2 in an index form, then plus 2 raised by the power of 3 in an index form, which is 8, meaning that I can rewrite my 14 in this way. Therefore, I'm introducing this in place of my 14. Then my question becomes 3 raised by the power of t plus 3 raised by the power of 2t as it is, plus 3 raised by the power of 3t, then equals to, instead of writing 14 here, my 14 has now becomes 2 raised by the power of 1 plus 2 raised by the power of 2, then plus 2 raised by the power of 3. And to be handled in a simpler form, I am going to say let p equals to 3 raised by the power of t. By so doing, it's going to make my work neater. Having this, then we can rewrite our question like this: p plus another p raised by the power of 2, then plus another p raised by the power of 3 equals to 2 raised by the power of 1 plus 2 raised by the power of 2 plus 2 raised by the power of 3. Collect the lighting times in terms of power. We're going to have p, which is the first p raised by the power of 1, when we bring in 2 raised by the power of 1, so we're going to have minus 2, 1. This plus is still there, then this p raised by the power of 2, bringing in 2 raised by the power of 2, it's going to be minus 2 raised by the power of 2, then this plus is still there, plus p raised by the power of 3, then this 2 raised by the power of 3 is going to become minus. By bringing it to the left hand side, we have 2 raised by the power of 3, but this time around equals to 0. Now if I write and group it under parentheses like this for clarity, p squared minus 2 squared, then plus p raised by the power of 3 minus 2 raised by the power of 3, under parentheses equals to 0. Now from this point, I'm going to need some mass identity. For this side, p squared minus 2 squared. Then for this side, p raised by the power of 3 minus 2 raised by the power of 3. If I have a square minus b squared, this can be written as a plus b, then a minus b. Then if I have a raised by the power of 3 minus b raised by the power of 3, this is going to be equal to a minus b, then a square plus ab, then plus b square. Now what as my equation becomes, I'm going to write this first. I have p minus 2, then plus b square minus 2 square. Of course, I'm not writing this directly again because it has turned to this expression, that is p minus 2, then p plus 2, then p minus 2. I can continue writing it as plus p plus 2, then p minus 2. Actually, this is for the first identity. I wrote the expression of p squared minus 2 squared, which is this. Now the next thing to write is to write the identity for p raised by the power of 3 minus 2 raised by the power of 3, which is what we've just written here. And this is going to become, we have p minus 2, then p squared plus 2p, then plus 2 squared, as it is earlier here. Then the next thing I want to do is to put it in the square brackets. Then I can see that some stuff are common here. P minus 2 is present here, p minus 2 is also present here, p minus 2 is also here. Now if I factorize out this common stuff, p minus 2 and p minus 2, then another one, p minus 2, what am I going to have and how is it going to look like? I am having p minus 2, then I have my square brackets. What is left here is going to be 1, then plus what is left around here is just p plus 2. That is what I have there. Then at this side, what do I have left? After this is gone, I have the whole stuff of this left, that is p squared plus 2p, then plus 2 squares is 4 definitely, so I have 4 here. Then I'm going to close my square brackets. So if I can open these parentheses, I can rearrange. Since I have plus all through, I don't have problem. I can open the parentheses and expose my figure. There's no problem. The whole sign that is there is just plus. By so doing, I can add 1 plus 2 making 3, then plus 4 making 7. I have 7 there as whole number. Then if I add p plus 2p, I have 3p there. So I'm going to be left with p squared that has no partner. So what I have left now, I can say p minus 2. Okay, then what do I have inside the whole stuff of these square brackets is p squared. I have p squared, then I have 3p, that is plus 3p. Then I have 7 plus 7, then I close that, and don't forget still equals to 0, equals to 0. At this point, this means that p minus 2 equals to 0, or p squared plus 3p plus 7 equals to 0. At the end of the day here, p equals to 2. Looking for the value of p here in this quadratic equation, definitely my p here is going to lead into complex number. So I'm going to take this, which is whole number, then for this complex number I am going to ignore. So with p equals to 2, which is whole number that we're going to work with, remember from the beginning we have assigned that p equals to 3 raised by the power of t, but p equals to 3 raised by the power of t, and p equals to 2 here, and p equals to 2. So we can continue by saying 3 raised by the power of t equals to 2. Applying logarithm, that is natural log to both sides, we can say we have log of 3 raised by the power of t equals to log of 2. Therefore, this power of t comes here. We have t log of 3 equals to log of 2. Dividing both sides by log of 3. What are we going to have? We're going to have log 3 cancel log 3. So t equals to log of 2 over log of 3. And we're going to note that if we have log a over log b, this can be written also as log of a base b. Applying the same thing here, we can say we now have log of 2 base 3. Therefore, t, the value of t is equal to log of 2 base 3. This is the final answer. Then we might need to verify if this value of t, log 2 base 3, is correct. Then we're going to need the same question. So wherever we find t, we're going to replace it by log of 2 base 3. In order to verify this answer if it is correct, that is this value of t, as said earlier on, we're going to replace every t here with log 2 base 3. That is, we have it now 3 raised by the power of log 2 base 3 plus 9 raised by the power of log 2 base 3, then plus 27 raised by the power of log 2 base 3. We want to see if this is going to be equal to 14. So if the left hand side equals to the right hand side, it shows that this value for t is actually correct. So to simplify this, we're going to need logarithm identity that says that if we have b, then log of a base b, this is going to give us a. This go for this. Applying the same rule here, we're going to have 2 here because this is going to go for this, plus we're going to write this 9 in an index form, that is 3 raised by the power of 2 log of 2 base 3. Then the same thing to 27, that is 3 raised by the power of 3 log of 2 base 3. Let's see if we're going to end up getting 14 or not. So this power, this 2 is going to come to the power of 2 here according to the logarithm rule. That is, if we have, let's say, log a to the power of p base x, this power is going to come to this place, which is b log of a base x, and that is vice versa. B comes here to become a power. Having the same thing, we have 2 plus 3 raised by the power of log of 2 raised by the power of 2 base 3, plus the same thing happen here, 3 raised by the power of log of 2 to the power of 3 then base 3. So definitely this is going to be 4 and this is going to be 8. So we still have these 2 here having some nice time. Then we have 3 log of 4 this time around base 3, then plus we still have 3 log of 8 base 3, log of 8 base 3. Then still checking if this will be equal to 14. So based on this power, then with this rule, just if we have it in this way, this is going to go for this end, the answer is going to be A. So this is going to go for this, then we have 4 left there, 3 go for this, then we have 8 left there. At the end of the day, we still have these 2 left here, 2 plus, then here we have 4 left, that is 4, then plus what do you have left here, that is 8, then is equal to 14 or not. So 2 plus 4, that is 6, 6 plus 8, the whole stuff here is 14, which is also equal to 14. That shows that this value of t is absolutely correct.